Good morning or good afternoon, viewers. My name is Professor Duke Orata. Today, we want to continue the thermodynamics lectures and want to look at fluid flow in an annulus. What is an annulus? So let us look at annulus. Now, when you're talking of annulus is that region between two concentric circles. It's the region between two concentric circles. So we can represent this diagrammatically in a simple manner. We can represent it as we have this circle. Let's have it here. Let's do the best. Let's see if we can do a better circle than that. Oh. Looks better. And then another one. Not the best, but reasonable. So let's say that the radius for that is y. This one is r. So we have the outer circle, and we have the inner circle. So this region here is the annulus. So we are considering the fluid velocity in this annulus there. So want to look at fluid velocity the annulus. Now, one of the first things which we work with, one of the first things which we remember is that we had said that the ratio of the velocities, that is along the axis, that's the ratio of the fluid flow along the axis, that for that cylindrical tube, and then the velocity in the distance along the y-axis or from the wall. We said that the equation for that is parabolic. It's parabolic. And once again, I encourage you to go through our earlier lectures where we have seen how we have come up with these expressions. So, assuming parabolic flow, for that particular fluid flow, parabolic equation, we have U, or UR equals to R now U R velocity along the axis, and that's important for us to note. So if we have this particular expression in terms of the parabolic equation depicting the velocity of that particular fluid, then when we talk of the mean velocity, the weighted mean velocity, we say that to obtain the weighted mean velocity, we'll have the expression like that, where rho is density, mu is velocity, A is area. Now, if we assume that this annulus, which we have, the width is dy. The width is dy. Then we can proceed and compute these other quantities very easily. So assuming the width of the annulus is dy. If the width of the annulus is dy, then now our life becomes a lot easier because we can get the expressions which we want. We have already said that u over ur is 2y over r, that's the parabolic equation, y over r squared. So that u is ur 2y over r minus y over r squared. Very straightforward. So we've just made u the subject and we have gotten that particular expression. And we are saying that to get the weighted mean velocity, which we designate as um, we simply sum over this particular quantity, take the integral. So if we take the integral, what we are going to get is the integral. So we're talking about we want to get the weighted mean velocity. So let's just do the integration. So integrate rho ur into 2, that's the parabolic equation, plus y r squared. And remember that what is the area? We have our area here is the circumference, 2 pi r minus y dy. That is 2 pi r minus 2 pi y. And these are remember, those are the two radii which we have put in those showing the radii of the two concentric circles. And the width is dy. So what do we have? We have rho um. We are starting from 0 to r, rho um as our limits for the integral. What are we having? Let's use this end here. So you're saying for this particular expression, we'll have r rho ur 2 y over r minus y over r squared 2 pi r minus y dy. So this in a nutshell is simply integral of rho the velocity, the mean velocity, to pi r y dy. Y dy. So solving for this particular integral, we have rho m into 2 pi r to r dy minus r 2 pi y dy. This of course vanishes. And so what do we have now? We have rho m into 2 pi. We are using the identity. Don't forget, let's remind ourselves, using the identity, the integral of x raised to power n is x power n plus 1 power n plus 1 plus c. We are familiar with this integral. We have used it. We keep using it. We have used it. We are using it, and we will still be using them extensively. So if we apply that one, that identity there, apply this identity, then we see that we obtain rho um into 2 pi y squared over 2 r naught. Of course, those two will cancel, so that we'll have rho to pi y squared r o. So if you open up this particular bracket, remember, just remind yourself that whenever we have that bracket, x squared, and you have r1. So opening up that bracket, we have x. Let's say we have x squared. Let's say we have x, so we'll have x squared, we'll have r squared minus 1 squared to open up this particular bracket here. When you're opening this type of bracket here, that's what we have there. So we have that as rho into pi r squared minus pi 0 squared. And of course that is rho into pi r squared. And of course, if you took those two ratios, take the ratios of the velocity along the axis to this weighted velocity. Remember, that is the weighted mean velocity. Take those two, take the ratio of the two, you will find that UR is simply half. It's simply half. Now, so we are able to find out, to compute, for example, this quantity, the mean velocity, in this annulus. You clearly see that we have the density, we have the mean velocity, and we have that value for that particular radius, which is very important. It is factored in that expression there. It is factored in that particular expression. Now, to compute now the shear stress on the wall, we'll find that the shear stress is m squared over 2. That is, remember, the weighted mean velocity. That's the shear stress. Those are the forces between the fluid and the wall. Don't forget that. And remember that earlier on, we had mentioned the shear stress, tau. That is tau. Let's just note somewhere. That is tau. So it's pronounced as tau. And that tau, which is for stress, shear stress, is normally mu dy, where this is dynamic viscosity. Or you can also express it as rho mu dy, where this V is kinematic viscosity. So the shear stress, the wall, this annulus, is gotten as F, the weighted mean velocity, divided by 2. What is F? F is the friction factor. And the friction factor, friction factor basically is a measure of those friction losses associated with this fluid flow. And that friction factor which you're going to use the Deci equation. It's actually Deci-Wehlbach equation, which says that the friction factor is F to the G. And what are those quantities there? So this is the Deci-Wehlbach equation for friction factor. F there, that equation, is Deci resistance factor. L is the length of the pipe. V squared, V is the mean velocity, which we have just computed. D is the diameter of the pipe. And G, the usual acceleration due to gravity. So even in terms of just the velocity in the axis of a tube, if you are looking at that and not looking at the annulus, then you can just use that ratio and you'll not be very, very far off from what you expected. So this friction factor, if we plug it in here, we can plug it into this particular equation, and of course you will see that it will be very, very interesting in terms of that. But you can see that the friction factor is inversely proportional to the diameter of that particular pipe, and of course is directly proportional to the length. You expect that because the fluid is flowing lengthwise, and so you expect that as you proceed, then you will be building up friction. And we had seen in our earlier lectures, and I encourage you to look at those lectures, we had seen that in the laminar flow region, if you look at the velocity profile and so forth, in the laminar flow region, the Reynolds number, which actually gives the ratio between the inertial forces and the viscous forces, is less or equal to 2300. But then as you continue moving on, and you probably develop velocity gradients in the fluid, then you're going to have turbulence. Of course, in a pipe, you're not going to initiate it. It will just take place at some point. And of course, it depends on, for example, the age of those pipes. Maybe there's a lot of silting on the wall, and so forth and so forth. But you expect that if it's just clear pipe, then it should move on freely. But otherwise, if there are depositions on the walls, those particular regions, they can act like a tabulator of sorts, initiate the turbulence process. And again, in those particular areas, now you find the Reynolds number is a bit enhanced, is greater than 2300. And so these are important things to know. So basically, the friction factor, you see, increases with length according to the Deci-Wehlbach equation, and also is it increases with the square of the mean weighted velocity. So we have seen that just to recap, annulus is that region between two concentric circles. What is concentric? It means they have the same center. They have the same center. Same center. So these two circles are concentric. And you have seen that we can compute actually based on our parabolic equation. Based on our parabolic equation, we can get expression for the mean or the weighted velocity, the fluid flow, and the annulus. And you have seen that we can the shear stress also can be computed, and we have used the Darcy equation, and we have seen that F there. Now remember, if you plug in that F there, then you get the bigger equation, and which we have already discussed, and say the friction factor. What factors influence that friction factor? That's the length of the tube, the diameter of the tube, and the mean velocity itself. So we shall stop at that particular point. We'll pick up from there next time.